about 650 light-years away from us, a ticking time bomb is quietly accumulating energy. When it explodes, it will unleash a blazing wave of radiation and burning material across the Milky Way, destroying everything in its path. Planets that are too close will be torn apart, their rocks melted into magma, and their atmospheres blown away. The remarkable thing is that this ticking time bomb is close enough for us to see it with the naked eye at night. It is one of the brightest objects in the sky, standing out among countless other stars. That is Betelgeuse, the giant red supergiant closest to us. And one day, in the not-too-distant future, it will become a supernova. But what does "in the near future" really mean? Centuries? Years? Or perhaps even sooner? And if it does explode, how will that affect Earth? To answer these questions, scientists have been monitoring Betelgeuse day by day, studying this unstable giant as it teeters on the brink of collapse, searching for any signs that might foreshadow disaster. Each new observation brings unexpected discoveries, revealing hidden secrets buried deep within the star's shrouded layers. You're watching Cosmic Light. In today's short film, we'll explore everything you need to know about Betelgeuse, including some astonishing recent discoveries. As always, let's start with the basics. Betelgeuse is the 10th brightest star in the sky, easily recognizable at the left shoulder of the Orion constellation. When you look at it, you'll notice it shines a deep red, more vivid than any surrounding star, shimmering intensely. This color perfectly matches its classification. Betelgeuse is a massive red supergiant, also known as a high-mass star. It is far larger than the Sun, and this case is no exception. Its radius extends beyond the orbit of Mars. Betelgeuse has a radius nearly 900 times that of the Sun. Yet its density is much lower, almost as if it were only about 10 times thicker than air. Because its mass is spread out over such a large volume, the surface gravity is extremely weak, almost incapable of holding on to its outer layers. As a result, gigantic convection cells constantly bubble across its surface. Imagine watching a sunset from such a colossal star. But the most important thing for many people is Betelgeuse's imminent collapse. Supernovae in our Milky Way are rare. Each year, astronomers observe hundreds of supernovae, but most of them are in distant galaxies, simply reflecting the enormous number of galaxies in the universe. In the Milky Way itself, only about 2 to 3 supernovae occur per century on average. This means the chance of Betelgeuse exploding tomorrow is low, but not impossible. And if it does happen, the impact will depend on the distance. Even more interesting, according to archaeologists, Earth has been affected by supernovae multiple times throughout its 4.5 billion year history. Today, we live in a region of space known as the local bubble, a relatively sparse interstellar zone about 1,000 light-years wide. This region was formed by a supernova explosion that occurred 10 to 20 million years ago. And Earth has existed within it ever since. Scientists have found evidence of another supernova that occurred around 2.5 million years ago. They detected it through unusual concentrations of iron-60 and manganese-53 in a specific geological layer. That explosion happened at a distance far enough to pose no danger to Earth, but that is not always the case. Some scientists even believe that the extinction of the woolly mammoth may be linked to a massive fragment from a supernova impacting our planet about 13,000 years ago. In fact, mammoth tusks dated to 34,000 years ago have been found with tiny impact pits caused by light radioactive iron particles traveling at speeds of up to 10,000 kilometers per second. This number is far from random, as fragments from supernovae typically range from 10,000 to 40,000 kilometers per second. An experience far from pleasant for massive creatures like mammoths. Re-examining the geological record over time helps us better understand Earth's long and tumultuous history. If life appeared on Earth around 3.7 billion years ago, and we have experienced 3 supernova events impacting the planet in the past 20 million years, yet life persisted, it is clear that supernova, in general, are not always as catastrophic as early warnings might suggest. But the main issue lies in the distance. If a nuclear bomb exploded 1,000 kilometers away from me, I wouldn't be afraid. But if it went off right on my coffee table, that would be a completely different story. Similarly, supernova follow the same principle. The universe has giant coffee tables we need to be mindful of. To understand their true destructive power, we must grasp the physical forces involved. This brings us to how massive stars reach their explosive fate. It turns out there are 2 main paths for a star to become a supernova, but both only apply to certain types of stars. The first path leads to a type Ia supernova, which typically requires a white dwarf in a binary star system, gradually accreting material from its companion star until it reaches a critical mass. This process is not yet fully understood, but essentially, the star's core is mostly carbon, almost like a giant diamond balancing 2 opposing forces: electron degeneracy pressure and gravity. In other words, the atoms in the core resist being compressed too much, creating a delicate equilibrium just before the explosion. The electrons in atoms prefer to maintain a certain distance from the nucleus, and they resist being squeezed closer than that distance. On the other hand, Gravity is an incredibly strong force, constantly trying to pull matter toward the center. This becomes especially significant in a dense mass like a white dwarf, where a tiny volume the size of a sugar cube can have the mass equivalent to a car. At this point, carbon fusion begins. In just a few seconds, most of the star's material undergoes fusion, forming heavier elements and releasing an enormous amount of energy. Up to about 1/4 decillion joules, a number followed by 45 zeros. Matter is ejected in all directions at roughly 6% the speed of light, while a massive burst of gamma radiation spreads across the galaxy. This event produces a brightness 5 billion times that of our Sun and lasts for several weeks, until the ejected material has traveled far enough for the overall energy to begin declining. For Type 2 supernovae, the process is similar, except it occurs in a massive star with at least 5 times the mass of the Sun, the type directly related to Betelgeuse. When the hydrogen fuel runs out, the core can no longer resist gravity. The core compresses, and fusion reactions with helium, oxygen, and neon produce heavier elements, pushing the star into the red supergiant phase. Like a Type A supernova, this delicate balance eventually collapses. This time because the star has exhausted its fuel. A red supergiant cannot fuse anything heavier than iron, so there is no fusion energy left to counteract the star's immense weight. Electron degeneracy pressure is insufficient to maintain the structure, leading to a violent collapse. The remaining core may become a neutron star or a black hole, while the white dwarf nearly vanishes completely. If Betelgeuse explodes, it will become one of the brightest objects in the night sky, easily visible to the naked eye. A dazzling, powerful spectacle, both beautiful and terrifying. A majestic testament to the colossal physical laws governing the universe. The scale of energy and matter released in a supernova is unimaginably immense. A nearby planet would stand no chance of survival. The energy is enough to tear a star apart, and any planet in its vicinity would be completely destroyed. Fortunately, our Sun does not have enough mass to become a supernova. If the Sun were to suddenly explode, Earth could partially or entirely vaporize. Outer rocky layers would reach temperatures 15 times that of the Sun's surface and be swept away in the following weeks. However, this level of destruction decreases rapidly with distance. In 2011, experts from the University of Cambridge calculated that even planets located about 15 billion kilometers from their parent star, 100 times the distance from Earth to the Sun, would remain intact, only being pushed out of their orbits due to the loss of gravitational pull. This demonstrates that supernovae are extremely violent close to the source, but their destructive power diminishes rapidly with distance. If we imagine a planet existing near a supernova, its ecosystem would face severe challenges. The light, sometimes brighter than an entire galaxy, could blind living creatures. And the stripping away of the atmosphere would have serious consequences. Intense radiation could destroy the ozone layer, increase the risk of radioactive poisoning, and wipe out plankton, triggering a chain reaction throughout the entire food web. Scientists estimate that the lethal zone extends within a radius of about 25 light-years. Beyond that, the energy disperses and diminishes. Asteroids from a supernova 250 light-years away could have impacts, but not catastrophic ones. Overall, we would remain unharmed if a supernova occurred at a great distance. The radiation would not be strong enough to cause mass extinction. At a distance of 500 light-years, we would almost only notice the star shining brighter in the sky. Betelgeuse is not a direct threat to Earth at present. So, what about within 300 light-years? Is there any other star to worry about? Fortunately, scientists are fairly confident that the answer is no. Giant stars are very easy to detect, and currently there are only two potential candidates: Betelgeuse and Antares, but both are more than 400 light-years away from us. More difficult to detect are white dwarfs, which gradually fade over time. However, thanks to ESA's Gaia Observatory, scientists identified around 13,000 white dwarfs within 326 light-years in 2013. Despite the large number, experts remain extremely confident that none of these stars is expected to explode in the next few 100,000 years. Thus, Earth is completely safe from the threat of a supernova. Shock waves from Betelgeuse would take hundreds of years to reach us, and by the time they arrive, their force would be much weaker than the solar wind. It is not the magnetosphere or atmosphere, but the heliosphere, the Sun's protective bubble that would block any impact. This means we would suffer no damage at all. Instead, we would witness a spectacular sight, a bright point in the sky, possibly as luminous as the full moon, even visible during the day. This means that Betelgeuse could take up to 100,000 years before it explodes. However, some scientists believe that this red supergiant could go supernova within the next few decades. Based on the hypothesis that Betelgeuse is larger than previously estimated, we might have an extremely rare opportunity to witness a supernova in our lifetime. But Betelgeuse is not easy to reveal its secrets. Over the past decades, it has continuously delivered surprises. The star brightens and dims in multiple cycles, ranging from a few hundred days up to 2,170 days. Yet scientists still do not know which cycle is fundamental and which are harmonics. This complexity makes Betelgeuse one of the most closely monitored stars. In 2019, Betelgeuse experienced the Great Dimming, a mysterious fading that captured the world's attention. From September of that year, Hubble detected hot material escaping from the star's atmosphere. As this material cooled, carbon dust particles formed, obscuring our view. By December, the southern hemisphere of Betelgeuse had noticeably dimmed. At its peak, the star was 2/3 dimmer than its usual brightness. But by April 2020, it had returned to normal, evidence that the dust had drifted away or dissipated. Betelgeuse does not fluctuate solely because of dust. A long cycle, about 2170 days, seems only explainable if Betelgeuse has a small companion star. This idea has existed for over a century, but no one has been able to prove it. Betelgeuse is so unstable that its constantly changing surface makes detecting a companion star nearly impossible. However, after the Great Dimming event, 2 independent research teams found evidence suggesting that this long cycle could be the signature of a sibling star. All of these mysteries, from the 15% contraction in 2009, the Great Dimming of 2019, to the strange long cycle, make Betelgeuse one of the most enigmatic stars we have ever observed. Each time we look again, Betelgeuse presents us with yet another question. The key to proving the existence of Betelbuddy, the affectionate name astronomers use for Betelgeuse's companion star, officially named Siwarha, lies in reanalyzing its motion data. 2 research teams, one from the Harvard-Smithsonian Center for Astrophysics and another from the Flatiron Institute, discovered a small repeating wobble. Betelgeuse appears as if it is being pulled to one side and then jerked back. What is peculiar is that this wobble coincides with the times Betelgeuse dims, suggesting that an object is exerting influence. The 2 research teams agree that Betelbuddy has a mass roughly equal to the Sun and orbits at a distance slightly less than that from the Sun to Saturn. If this is correct, Betelbuddy is the missing piece in the Betelgeuse puzzle. Efforts from space yielded no results. So the team at Gemini North took a different approach. They used an 8.1-meter telescope combined with a speckle camera, capturing thousands of extremely short exposure images to overcome interference from Earth's atmosphere. They aimed at Betelgeuse at exactly the time Betelbuddy was predicted to be at its farthest position, and they saw it. A faint object 6 magnitudes dimmer than Betelgeuse, located just below the resolution threshold of the Gemini telescope. Although it cannot yet be considered conclusive evidence, the observations and predictions all align. However, we will need to wait until 2027 when Betelbuddy reaches its farthest position from Betelgeuse to confirm it. If proven, this will be a major breakthrough in deciphering this red supergiant star. If Betelbuddy is confirmed, it means that the 2,170-day cycle is not Betelgeuse's fundamental cycle. The consequence is, the big explosion may still be a long way off. For those hoping to witness a supernova in their lifetime, this is probably disappointing news. But for Betelgeuse itself, it is good news, because when Betelgeuse explodes, this small star would be within the deadly danger zone. But even though it's unclear when Betelgeuse will explode, one thing is certain: this star is completely abnormal. ALMA shows that Betelgeuse completes a rotation in just 20 years. Given its enormous size, this corresponds to a surface speed of about 18,000 kilometers per hour, nearly 5 kilometers per second. Betelgeuse's rotation speed reaches 5 kilometers per second, 10 times faster than the surface speed of Earth. A figure that almost defies the laws of physics. But how do we know this? Directly observing the surface of Betelgeuse is impossible. The star is 650 light-years away, with an angular diameter thousands of times smaller than Jupiter's. Even through the most powerful telescopes, Betelgeuse appears only as a faint smudge. Fortunately, there is another method, using the Doppler effect, the principle that makes a siren change pitch as it approaches or moves away. Light from the part of Betelgeuse moving toward us is slightly blue shifted, while light from the part moving away is slightly red shifted. Analyzing these color differences in the spectrum allows us to determine the rotation direction and calculate the surface velocity. This is how ALMA measured Betelgeuse rotating at about 5 kilometers per second. However, there is a problem. According to the physics of red supergiant stars, a speed of 5 kilometers per second is almost beyond the limit that Betelgeuse can sustain without disrupting its internal structure. This is a mystery that astronomers are still investigating. Let's take the Sun as an example. Its rotation speed is about 2 kilometers per second. But if it expanded to the size of Betelgeuse, nearly filling the entire solar system, its rotation speed would drop to just 2 meters per second. If we then added mass to match Betelgeuse, it would be only 0.2 meters per second. A plausible hypothesis is that Betelgeuse accumulates angular momentum through a process called stellar cannibalism. The star absorbs gas from a companion star carrying angular momentum, which makes it both larger and rotating faster than it would naturally. However, a recent study suggests that Betelgeuse might not be spinning rapidly at all. Data from ALMA may only be detecting the blue redshifts caused by giant gas bubbles on its surface. Each bubble could be up to 100 million kilometers wide, moving up and down, creating regions of light that are Doppler shifted. Thus, Betelgeuse's unrealistic rotation speed might be nothing more than a giant optical illusion. This red supergiant keeps its own secrets, and astronomers continue to debate. Is Betelgeuse truly spinning fast, or is it all just the product of its chaotic surface? Therefore, it is possible that astronomers have misinterpreted the frequency shifts they observed as a result of rotation. In reality, Betelgeuse's boiling surface could create random blue-red patches, making the Doppler effect appear like the smooth spectrum of a rotating star. In an ideal world, the color spectrum would correspond to rotation. But Betelgeuse is too far away, and the images from ALMA are not perfect. When scientists simulate the surface with resolution limits, they find that the gas bubble patches can be mistaken for a rotational gradient in up to 90% of cases. The good news is that there are images taken with longer exposure times, allowing for more detailed surface analysis. The bad news is that those who are impatient may have to wait several years for the full results. So, does Betelgeuse really spin at 5 kilometers per second after devouring its companion star? Or will the new claim that this speed is merely an optical illusion be proven correct? This remains an open question for astronomers. You now know almost everything there is to know about Betelgeuse, a star on the brink of catastrophe. It's no wonder that such a cataclysmic phenomenon leaves us both awestruck and fascinated. Humans have always been fascinated by explosions, as fireworks festivals prove. Whenever Betelgeuse goes supernova, it will light up the night sky, a spectacular sight to behold. Thank you for watching the video. Keep exploring the mysteries of space with us, marveling at the beauty of celestial objects and enjoying moments of relaxation amidst the rush of life. Don't forget to subscribe to the channel and hit the notification bell so you won't miss any cosmic journeys with cosmic light.